Welcome to Demystifying Equivalence Relations. In this presentation, we will build a full conceptual arc, starting with basic binary relations, then isolating the three properties that define equivalence relations, and then connecting those properties to partitions, equivalence classes, and real applications. The visual with three linked hexagons is intentional. Reflexive, symmetric, and transitive behavior work together as one integrated structure. As we proceed, keep one central question in mind. When can we say two objects are essentially the same for a specific purpose? Equivalence relations answer that question with mathematical precision. By the end, you should be able to move comfortably between formal definitions, intuitive examples, and practical uses in number systems and computation. We begin with the foundation, binary relations. A binary relation on a set S is any subset of S cross S, meaning it selects certain ordered pairs and excludes others. On the left, you see the full universe of possible pairs. On the right, only selected links are active, which defines one particular relation row. The notation x row y is shorthand for saying that the ordered pair x comma y belongs to row. This matters because every specialized relation, including equivalence relations, starts from this exact setup. So the key idea here is selection. From all possible pairings in S cross S, we keep only the pairs that satisfy the rule we care about. Now we define equivalence relations as a special class of binary relation. Not every relation qualifies. To be an equivalence relation, the relation must satisfy exactly three properties: reflexive, symmetric, and transitive. The column visual emphasizes that each property is a required support, not an optional feature. If one support is missing, the structure fails and we no longer have an equivalence relation. Conceptually, these three conditions enforce consistency in how sameness behaves. Reflexive says each element matches itself, symmetric says matching is mutual, and transitive says matching chains together coherently. Together, they produce the exact logic needed for stable grouping. This slide states the three required properties in formal notation and plain language. Reflexive means for every x in S, x is related to itself. Symmetric means if x is related to y, then y must be related to x. Transitive means if x is related to y and y is related to z, then x must be related to z. The diagrams underneath each formula show the same logic as loops, two-way arrows, and chained arrows. These are not just technical conditions, they prevent contradictions. Without reflexivity, we lose identity. Without symmetry, we lose reciprocity, and without transitivity, we lose consistency across chains. Equivalence relations are exactly the relations that preserve all three. Let us ground the definitions with a classroom example. Let S be the set of students, and define x row y to mean x sits in the same row as y. Reflexive is immediate. Every student sits in the same row as themselves. Symmetric also holds. If John sits in the same row as Judy, then Judy sits in the same row as John. Transitive holds as well. If John is in Judy's row and Judy is in Ted's row, then John is in Ted's row. This example is useful because it is visual and intuitive, but it is also mathematically exact. Same row relation satisfies all three properties, so it is an equivalence relation. Once we have an equivalence relation, the set naturally breaks into a partition. A partition is a collection of subsets called blocks that are non-empty, pairwise disjoint, and whose union gives back the original set S. Rule 1 on this slide is disjointness. No element appears in two different blocks. Rule 2 is union. Every element of S appears in some block. The classroom interpretation is straightforward. Each student belongs to exactly one row, and all rows together account for every student. This structural result is one of the most important outcomes of equivalence relations because it turns pairwise relation data into a clean global decomposition of the set. Each block in a partition is called an equivalence class. For an element x, the class bracket x bracket is the set of all y in S such that x is related to y on this slide. The class named by John includes John, Chuck, Jose, Judy, and Ted. A key insight is that any member can name the same class, so bracket John, bracket Judy, and bracket Ted represent identical sets here. This naming flexibility is important in practice. Class labels are representatives, not distinct objects by themselves. Always separate the symbol used to name a class from the underlying set the class actually contains. This is the fundamental two-way theorem. Direction 1. Every equivalence relation on S determines a partition of S into equivalence classes. Direction 2. Every partition of S determines an equivalence relation by declaring two elements related exactly when they lie in the same block. So equivalence relations and partitions are not separate topics. They are dual views of the same structure. One view is relational, based on ordered pairs and properties. The other view is set theoretic, based on grouped subsets. In advanced work, you choose whichever view simplifies the problem, then translate back when needed. Here we enter the proof that an equivalence relation induces a partition, starting with the union property. Take any element x in S because the relation is reflexive, x is related to itself. Therefore, x belongs to its own equivalence class bracket x. Since x was arbitrary, every element of S belongs to at least one class. That immediately implies S is contained in the union of all classes, while the reverse containment is automatic because classes are subsets of S, so the union of all equivalence classes is exactly S. This step guarantees coverage. No element is left out when we form classes from the relation. Now we prove disjointness in the precise sense used for partitions. Two classes are either disjoint or identical. Assume two classes overlap. So some element y belongs to both bracket x and bracket z from y and bracket x. We have x related to y from y and bracket z. We have z related to y. And by symmetry y related to z, then by transitivity, x is related to z using the same logic in both directions. Every element of bracket x belongs to bracket z, and every element of bracket z belongs to bracket x, hence bracket x equals bracket z, so overlap cannot happen between distinct classes. If overlap occurs, the classes are the same block. This slide explains why the partition viewpoint is powerful. At the lower level, we may have many individual elements and many pairwise relations. By abstraction, we collapse each tightly connected family into one class-level object. The top layer shows these classes treated as coherent entities with simpler interactions. This reduction is a core mathematical strategy. Replace complicated micro-level detail with well-defined macro-level units that preserve the relevant structure. Equivalence relations are exactly the tool that justifies this compression without losing correctness. In short, abstraction through classes makes problems easier to reason about while staying faithful to the underlying data. Application 1 is rational numbers. A rational number is not a single fraction string. It is an equivalence class of fraction representations. We define a over b equivalent to c over d when a times d equals b times c with non-zero denominators. Under this relation, 1/2, 2/4, and -1 over -2 all represent the same class. Arithmetic on rationals is therefore arithmetic on classes, typically implemented by choosing convenient representatives. That is why we can compute with familiar forms, yet still refer to a single mathematical object. This perspective removes ambiguity and explains why many syntactically different fractions encode the same rational value. Application 2 is congruence modulo, and we say x is congruent to y modulo n when x minus y is divisible by n. This relation partitions all integers into exactly n residue classes. Bracket 0 through bracket n-1. The slide's modulo, for example, shows those classes explicitly, each containing integers with the same remainder upon division by 4. Congruence modulo n is an equivalence relation because reflexive, symmetric, and transitive properties all hold under divisibility. This framework is foundational in number theory and cryptography, where we reason about remainders instead of raw integer magnitude. Here is a practical computing use case. Real machines have fixed-width integer storage, so arithmetic that exceeds the maximum representable value overflows. Modulo arithmetic models what the machine keeps, the remainder after division by a modulus tied to word size. In the equation x plus y equals qn plus r, the stored value is r, the residue class representative. So even though the full mathematical sum may exceed capacity, the system remains consistent within modular classes. This is why wraparound behavior in low-level systems is not random failure, but structured arithmetic in an equivalence class setting. Understanding this prevents logic errors in systems programming and security work. To close, keep this cheat sheet map in mind. The properties are reflexive, symmetric, and transitive. The core concepts are partition, equivalence class, and the fundamental two-way theorem between relations and partitions. The major applications we covered are rational numbers, modular congruence, and computer arithmetic under fixed limits. If you remember one unifying message, let it be this: equivalence relations formalize meaningful sameness, and partitions expose the resulting structure. Moving fluently between formulas, class intuition, and real applications is the practical skill this topic develops.